Hello, my name is Arya Peruma from the Coding for Young Minds community organization, and today we're going to be talking about a more complex but very beneficial topic in Python, computer science, and machine learning, which is linear regression. So today we'll be learning many things. So we'll be learning the benefits of this, real-life situations where it can be used, and we're also going to be learning about something really exciting called Python libraries, which we're going to be applying this concept of linear regression to. So let's get started. So essentially, we have to first think about what linear regression is. So if we look over here, linear regression is basically when we're given data. So say you're given any set of data, usually it would be organized in a table like this with x values and y values. So exactly how you would see points plotted on a graph. So essentially, as you can see, there's x1, x2, all the way to xn. Xn is essentially just the last value, and y1, y2, all y values as well. So you're given a set of data, and essentially all of these values are all known values in our data sets. So essentially, when we are modeling this and kind of utilizing the idea of linear regression, the data set can be demonstrated through a scatter plot. So as you can see, I have an example written on the left, and the example has various x and y values. So it's basically like 0, 1, 2, 1 on the x side, and then 1, 3, 2, 2 on the y side. And what I've done on the right is I basically just plotted these, and I've not connected anything, but I've just plotted these data points. So as you can see, I've also written the data points out here. So as you can see, this is a very vague example of linear regression. So what we do is we take the data points that we are provided and we try to create an accurate representation of the data to the best of our abilities. So basically the objective of linear regression is to create a model that can predict the value of y of a new example if the value of x is known. So I'll show everyone a few examples of this. But before I do, I want to show everyone and bring to everyone's attention features and labels. So features and labels are two very crucial aspects of machine learning and terms that you will most likely hear a lot. So in machine learning, the x variable is called the feature and the y variable is called the label or target. Most often it's called the label, but target is also an appropriate name as well. So as you can see, we have x values, y values. X is features, y is labels. So that's just important to remember. And now when we talk about linear regression is basically a method to create a mathematical model that will demonstrate the relationship between labels and features, therefore creating a model that predicts the general direction of a data set or a pair of data points or multiple data points. So basically, as I mentioned before, we just want to be able to create an accurate representation of our data. So if we have a bunch of points, like I did over here, as you can see, it's a bunch of points. When you get into more complex data science and machine learning problems, it's most likely that you'll have hundreds, even thousands, and sometimes it can be 10,000s, even millions of different types of data points and data sets. So essentially with those sets, obviously since they'll be very mismatched all around the graph, as you can see, it's very scattered right now, but the more data you have, the more likely it'll be scattered even more, these points. So essentially, in order to make sense of the data and draw some appropriate conclusions from these millions or thousands of points that you see on a graph, we need to be able to utilize linear regression to kind of get the best accurate prediction of our model. So essentially, I've included an example of linear regression here, and it's essentially a very simple example to get you accustomed to what it's all about. So let's assume our model to be a straight line. So as you can see, I've drawn out a graph here, and there's two straight lines. You can see a red line and a green line. So let's pretend these are straight lines that are in the form of y equals mx plus b. And if you've attended some of the previous tutoring sessions, you would know that y equals mx plus b is the form of a straight line. And essentially, the label, which is y, as I mentioned before, is what we consider to be constant. So it's not variable, it doesn't fluctuate, it's just one constant value throughout. and m and b are both numbers. So where m is the slope and b is the y-intercept. So I believe some of you may already know this, but when we talk about straight lines and the form of a straight line, m is the slope of the line and b is the y-intercept. So as you can see, I'm basically taking those 4 data points that we had in the previous example I just showed you guys, and I've just plotted those once again. And now I've drawn 2 lines, red line and green line. So as you can see, we can conclude from this that the red line is a better model to represent data, and I'll tell you guys why. So essentially, when we talk about linear regression, we want to find something called the line of best fit. So I'm sure some of you may be familiar with this already, but if you're not, no worries. The line of best fit is basically the line that you draw through a set of data points. And basically, you want to get that line as close as to as many data points as possible. So the ideal situation is to basically draw a line and have that line touch every single data point in your set. But of course, in many times, this will not be possible, especially considering if there are millions of data points or even more. And essentially, what linear regression will enable you to do is it'll enable you to draw a line through your data points and try to get a closest possible match to all the points. So as you can see, this green line is not that accurate of a representation, as it does not come as close as possible to all of these 4 data points. However, the red line is a better representation as it comes closer to all the data points, and therefore we can see that this is a better prediction. In addition, I want to bring to everyone's attention that depending on which line or which model that you do pick, you will get different predictions for the labels. So let's say that we have feature 2.5. So remember, features are the x values. So I'm just written 2.5 in red. So on the x-axis, we have 2.5. If we take the red line as our model predictor, as you can see, the data point will be 2.5, 3.1. So the corresponding label to the feature of 2.5 will be 3.1. On the other hand, if we used the green line as our prediction model, we have 2.5 as the feature and 2 as label. So as you can see, even though the feature is the same, the labels, the predicted labels for both the red line and the green line are different because of the fact that one is a more accurate representation of the model overall than the other. So essentially, the conclusion that we can draw from this is that different lines enable us to make different predictions. And we want our model to be the line that goes as close as possible through all our data points. So now I want to tell everyone a continuation of what I basically said in the previous slide. And this is just continuing linear regression. But when we actually do this linear regression, as you can see, there's many possibilities for error within our predictions. So if I go back up here, even this red line is not perfect. It's better than the green line in terms of predicting the model, but even this is not 100% perfect. So no matter what you predict, there's always going to be a bit of error. It's not going to be 100% accurate, but there's always going to be sources for error. And that's what we need to figure out. So that's what I have over here. This is basically how to figure out how much error is in your prediction and how far off basically your prediction is. So it's basically a way to determine if your prediction is accurate enough or not. So as you can see, I've drawn another graph over here, and these black dots are our data points. So this black dot, and this black dot are all data points. I've drawn 2 lines, a red line and a blue line. So basically, these 2 lines are once again supposed to try to act as model predictions for our data points, those black data points. And basically, what we're trying to do is we're trying to figure out how far off our prediction was. Let's take this red line for example. So essentially, we're going to just label these data points as x2, y2, that's the first data point, x1, y1, second data point, and finally, we just have this one, which I haven't labeled because we're going to be focusing on these two to figure out the sources of error within the first 2 points. So essentially, when we try to figure out how much error there is, we basically need to compute the distance between the features. So features are y values. So if you see over here, this green line between the red line and the black data point is the error in our prediction. So that's basically how far off our prediction is from the actual point itself. So to actually find this out, we need to do y hat 2 minus y2. Y hat 2 is basically um, the shared label but different feature. So basically it's correspondent, the label is correspondent with the actual data point itself, but the feature is different. So we take the feature of that red line that we predicted minus the feature of the actual data point that we have. So what we do to predict the error is we have to subtract the two. So we do y hat 2 minus y2, and this will give us a negative result since y hat 2 is a lower number. So we just put that in absolute values, or we can alternatively do y2 minus y hat 2. And just finding the difference, we can see the distance of this green line, which will give us the error. So therefore, from this, we can say that the error is y hat 1 minus y1 squared plus y hat 2 minus y2 squared plus y hat 3 minus y3 squared all over 3. And basically what this is called the mean square error, which is often denoted by the letter J. So the mean square error is basically the amount of error, or kind of how far off you were in your prediction. So as you can see, this green line denotes how far off I was in my prediction. This green line over here denotes how far off I was in this prediction, and so on. And basically to find just to find the error, we need to be able to calculate the average of all our separate errors. So that's what the mean square error is. So from this, we derive the general form of the mean square error as j equals 1 over n times y hat 1 minus y hat y1 squared plus y hat 2 minus y2 squared plus, and then all the way to whatever our final number is. In this case, it was 3, but depending on how many points we do have, it would be y hat n minus yn squared. So all this is we just compute the differences between the labels and the features, which we have over here. And then what we have to do is we need to be able to subtract those, find the differences. So basically we have to find the distances between the green lines, find those distances, and then find the average. So basically divide it by how many data points there were, just as we would find average regularly. And this is very helpful for finding the possibility for error within a given prediction. So now that we've kind of considered and discussed a bit about linear regression in Python and linear regression in general, we're going to be now discussing more specifically into the computer science aspects of this. So we just discussed the mathematical aspects, which was kind of learning what linear regression is, line of best fit, and how to calculate possibility for error. But now what we're going to do is we're going to be kind of going into linear regression with Python programming language. So before we do go into this, I did mention at the beginning of this tutoring session that we are going to be discovering Python libraries today. And we're going to be using this concept of linear regression, and we're going to be integrating that with various Python libraries. So Python libraries are basically a set of modules that are pre-developed for specifically the Python language. And examples of this, there are many examples, but some are Numpy, Pandas, and Keras. And essentially, Python is very unique from different coding languages such as Java or JavaScript or HTML, because in the sense that we have to actually be able to tell our program which library we're going to use and what blocks of codes we're going to be pulling from different strands of the language. And basically, what we're going to be doing today is we're going to be exploring 3 different main languages. So NumPys, Pandas, and Matplotlib. And we're going to be exploring these 3 libraries, and we're going to be figuring out how to use linear regression by integrating these libraries. So we're going to first start off by learning NumPy libraries and how to integrate that. So let's go over here to our code. And now, as you can see, we have our code over here. So I'll just resize this to make it a bit bigger for everyone. And now hopefully everyone can see this code. So what I did first is I imported the libraries. So as I said before, we're going to be using 2 main libraries, which is NumPys and Pandas. And I said 3 actually, so NumPys, Pandas, and Matplotlib. But we haven't gotten to Pandas and Matplotlib yet, but we'll get to it at the end of this tutoring session. So essentially, what I've done first is I just imported our library. So I've imported NumPy as NP. So we basically say as NP. So when we call this library again in the future in the process of our code, we can use this very short abbreviation instead of typing this whole thing again. So I'm going to change this to NP. So essentially, I've just imported these libraries. So what I'm going to do is I'm going to basically bring everyone's attention to this block of code over here. So basically bring your attention to this, and I'm going to explain to everyone what this means and what this has to do with linear regression. So let's go back over here. So basically this is the code that we just saw. As you can see, this function is basically something that takes the input of 2 lists that are of the same length. And basically the lists both contain labels and features, and they both have X and Y variables to them. So basically the output of this are 6 numbers that we call A11, A12, B1, A21, A22, and B2. And basically these are the coefficients of the linear equations. Basically these are M and B, and M and B, as we know, are the slope and y-intercept of the line. And basically what we're trying to do with this piece of code is that we're trying to find the line that best fits the data with this piece of code, just as I showed you guys the mathematical example at the beginning of this tutoring session. So going back to our code over here, as you can see, we have that same block of code. So what I'm going to do is I'm going to show everyone something called Numpy, which I discussed previously that it is a library, but I haven't really discussed Numpy arrays and why Numpy is so useful to be integrated. So let's do that right now. So essentially what I'm going to do is I'm just going to add another block of code to demonstrate this. And I'm just going to bring this up a bit. And we're just going to put it here. So what I'm going to do is I'm going to create 2 lists. So if you are familiar with Python, and if you have attended some of the previous Python tutoring sessions, I did go over lists and arrays and all of these really useful components. However, just for a refresher, I'm going to be creating 2 lists right now. So first is list X. So this is going to be 0, 1, 2, 1. And now I'm going to be also creating list Y, which is going to be, let's say 1, 3, 2, and 4. And you can put spaces between the commas if you want. Just to keep it more condensed, I'm just going to remove those, but those wouldn't make a difference in our code. So essentially, what we're going to do now is we're just going to take a look at this list right here. So the great thing about NumPy is that there's something called NumPy arrays. And basically these arrays allow us to tell us the indices, and they allow us to actually effectively correlate our data to our lines and to our graph as well. So if I see this list right now, as you can see, it's a list. But when we do when we actually try to figure out what kind of Python code it is, I'll demonstrate that right now. So when you type this, and I try to run it, as you can see, it will take a very long time to compute and eventually give us an error, as you can see. And the reasoning for this is because of the fact that it is not a NumPy array. And the only way that you can actually define x, as you can see, since x is not defined, the only way you can actually define it is to create an array. And that's why NumPy is so beneficial. So what we're going to do is we're going to now once again try to add that NumPy array in. So I'm just going to do x equals np dot array and then square brackets, and then just going to copy and paste that into this. And then likewise for y as well, we have y equals np dot array and square brackets, and we're just going to copy and paste all of these points. So now this should be good. And don't worry about this for now because we haven't really called anything. So essentially what we're going to do is we're going to run this NP so it recognizes our libraries. And now what we're going to do is we're actually going to be able to figure out if this is an appropriate form of instantiation for our code. So in order to do this, what we have to do is we have to follow through with linear regression and want to make sure that this is converted to an array. And now this is indeed a NumPy array, as we do have the instantiation of our NP and our np.array. And basically, as you can see, if I hover over it, it tells us what kind of library that we are using. And I've instantiated NP as the array. So I'm just going to get rid of this. And as you can see, the error is now gone because I just ran the library. So now what we're going to do is I want to show everyone something. So let's add another piece of code. So essentially, when I do something in a list, so let's try to print x times x in a list. So when you print this in a list, what actually happens is that it shows me an error if I try to do it in a list. So let's see. So we've instantiated our NumPy arrays, so it's now giving us it properly. But let's see what happens if we try to remove this. So I'm just going to copy and paste this and keep this somewhere else. But now I'm just going to remove this NumPy array. And now let's see what happens if we run it. As you can see, the list is not efficiently instantiated as it was with the NumPy array. So what we want to do now is we want to actually be able to introduce that NumPy array back again, which I'm going to be adding again. Now we're going to bring it down. So essentially, the purpose of this x times x, which I printed, was essentially to give us the sum of, basically give us the square of the labels. So essentially, it computes the square of the components of x, and it does this component by component. So I've already instantiated the NumPy array, so it will no longer give me an error as I wanted to show, but no worries because we already know that because of the NumPy array, we're able to effectively get the results element by element. So I'm just going to remove this list since it's no longer necessary. But essentially, the instantiation and the introduction of the NumPy arrays allowed us to effectively get the elements all transcended, and we're actually allowed to now see the square of the components of x. So we have 0 squared, 1 squared, 2 squared, and 1 squared. As you can see, square of all the elements, which is what has been printed. So now I want to do another function, which is going to be y_sum. So now let's try something else. So we have to do print, and now we're going to do print y.sum, and basically this is like a function. So we're going to run this, and now as you can see, it says 10. So when I do this, it basically renders through all elements of the array y and calculates the sum. So now it's doing 1 plus 3 plus 2 plus 4, which if you do mental math or calculate it, you will get 10. So essentially, the NumPy array allows us to effectively render through all elements of the array and compute computations. But in a list, we could not do that. In a list, it would give us an error. So what I want to do now is I want to now bring us back over here to explain something very crucial. So let's go back and let's go back over here. So now I want to introduce to everyone something called datasets. So essentially, datasets are basically spreadsheets of data. They're usually obtained from the professionals in a specific field. So for example, if you are looking at a dataset for age relation to type of cancer, you would obtain that from a medical professional or someone who is in the field. So it's basically a professional piece of data that has labels and features. And some of the times it has multiple features in it as well. So basically, this is a file that's basically obtained in a CSV file most of the time. And CSV file is basically like an Excel spreadsheet. And basically, datasets is basically just a spreadsheet. It's not a specific type of code per se, but it's just data, as it's in its name, dataset. So it's just data that's in a spreadsheet that we can then use and draw conclusions from with our code. So it's basically a very useful resource that we can use. So I'm going to actually try to show everyone a data set right now. So let's go back over here. And as you can see, hopefully you guys can see this data set. I'll enlarge it a bit. So let's get rid of this blue highlight. All right. So now, as you can see the data set over here. So I'm going to be explaining to everyone what this data set means and what we're going to be using it for today. So as I mentioned at the beginning of this tutoring session, we are going to be applying a lot of these concepts to real life. And let's start with that today. So essentially, to apply this to real life, I basically have a data set which has been collected from an online source. And essentially, we have the population and the profit. So basically X is population, Y is profit, label and feature. So what we're going to do is the population, and just keep in mind that although it does say 8.57, this is actually in thousands. So the population in thousands, and basically the correlation of that to the profit in thousands of that specific city. So when the population is this, the profit is this. The population is this, profit is this, and so on. So it's basically a correlation of independent and dependent variable, and it gives us a good sense of labels and features and the relationship between the two. So now that I've explained and taken a look at this data set, we have to get ready to use these in our code, as it's something that's very prevalent in machine learning, especially when considering predicting specific aspects of models. So in order to actually predict something, we need data to predict it for. We can't just predict nothing. We need kind of a framework set in place so we can draw our line of best fit and use linear regression to predict the best accurate representation of our data. And basically, these are like data points. So 6.1101 and 17.592 can be plotted like X and Y on a graph. So, all right, so that's great. So now what we're going to do is we're going to go back here. And before we do get started with these data sets, I do want to actually give everyone a very brief introduction to pandas as well, which is another library that we can use today. So now that we've learned a bit about these NumPy libraries and datasets, we have another library called pandas. And essentially, pandas is another library which was pre-written by someone specifically for the Python language, such as NumPy was. But essentially, it's a bit different because it gives us something called data frames. And pandas are very useful, specifically when we're working with data sets. NumPys are more for just the general relocation of our Python libraries, and it just gives us more flavor of the libraries, and it just gives us more context on what Python can really do. However, pandas is really closely integrated with data sets and how it can work with specific data sets as well. So let's go back to our code so I can demonstrate this to everyone. All right, let's go back here. And now, as you can see, we have this code. We have the sum of the y's computed. We have squares of x computed. So now we'll be able to find the line of the best fit using our coefficients of x and y. So now what I'm doing is from my Google Collaboratory, which is kind of the program I'm using right now, I basically have this data file in my Google Drive, and I've just uploaded it or imported that data set into this code. And after that, what I did is I imported pandas as PD. So PD is basically the abbreviation for pandas. Basically, we can import the library in this way. And now what we're going to do is we're going to basically use this data file, which is what I said before. I said pandas have something called data files, which is something that allows our code to read and scan specific sets of data. So we're going to say data file is equal to pd.read. PD is the abbreviation for panda, so it's panda.read. And as you can see, even if I hover over PD, it tells us the description of libraries. This is just a good way to check to make sure that we are indeed using the correct library. And if you decide to carry on with this and do some more practice and use Google Collaboratory in the future, this is a very useful tool that will actually allow us to see the features and the components of pandas. So basically, it integrates very nicely with NumPy. It has data frames that align data for our computations, which is perfect for what we're trying to do today. So basically, I'm reading the data file, and the data file I have is through this link. So that was this, and basically this link contains my data set, and I'm just analyzing that and scanning it with the Panda library. And now the df.head function, all this does, it basically just prints out our data set. So of course there was way more columns as you can see, but just for the sake of simplification, it's just shortened it a bit, but inherently it is continuing. So now that we have learned a bit about libraries, I want to now bring everyone's attention to this over here. So basically this over here, let's close that. This over here, the x equals df population.values, and the one underneath, the y equals df profit.values. The x is population, the y is profit, so corresponding labels and features. And basically it's very, very easy to change these sets of data into NumPy arrays, which is what I've done over here. As you can see, this is the data frame, which is provided by the pandas library, and basically the values of our data, and then finally the two corresponding columns, which are population and profit. And through this, we've easily, seamlessly brought this into a NumPy array. So we can make it easy for analyzation and calculation, as we know that if it's in a list, it's very difficult to calculate or nearly impossible. So now this is the part that we actually get into the linear regression portion. And in order to actually plot the line of best fit to predict your model, as we learned with linear regression at the beginning of this tutoring session, we need yet another Python library called matplotlib. So going back here, we're going to now look at something called matplotlib. So let's actually go back to our code. So essentially, matplotlib is a another Python library such as Numpys or pandas. But basically what matplotlib does is it allows us to actually graph our data points and data sets. So it's basically a library that allows us to plot our data. Essentially allows us to graph it. So it's very useful for graphing, and graphing is something that happens extremely frequently in the world of data science and machine learning, especially to get a very accurate representation of models and to predict the direction of very complex topics as well, such as cancer prediction or whether it be or like stocks or anything else like that. So basically, as you can see, I've imported this matplotlib.pyplot, which is library as PLT. So that's just the abbreviation for this. And now what I've done is from that data that we had and from that data that we imported with the help of the pandas library, what we have here is we're going to just use the plt.plot feature and plot the x and y points, basically ko marker size equals 2. So ko basically instantiates that we want it to be in terms of points rather than a really messy data graph. So what I mean by this is, let's just try to remove this. So I'm just going to take this off, copy that so we don't lose it, but add that back in. Let's try to run this. So as you can see, it does give us an error as this is now not defined. Let me try to bring this back. And let me try to run this. The Python or the matplotlib library was not run, so let me try that again. And now, as you can see, it works now. So I'm going to try to remove that KO again. Let's remove that. And now, as you can see, it gives a very messy representation of our data. So as you can see, this is not at all a straight line, or we can't really draw any conclusions from this. And the more data we do have, the more messier it does become. So it's really important that we do try to make it as simple as possible so we can draw an accurate representation. So that's why we have those things added in. So let me try to add those back in. So let's run that again. And just remembering to run my matplotlib library so it effectively graphs. And now as you can see, the KO, the O basically is what allows us to bring this into points rather than that really messy representation we just saw. And the K is basically just to change color. So if I did like RO, you would see the points are red, and then like BO, blue, and I'm not sure if this would work. Yeah, I guess that's not a feature, but of course there's many other things that you can do. So I'm just gonna keep it black for now, but that was just to show you guys the power of matplotlib. And especially in the data science world, many things do need to be coordinated either by color to recognize the features and labels correspondingly. So matplotlib does provide all of those functions in order to create these effective representations. So, and marker size in this is basically just the size of the points. So we don't want the points to be too big, so I've just kept them size 2, which is fairly good size. So now, as you can see, we just have those points, and we have gotten rid of the unorganized data that we had previously. So in any line of best fit, the prediction is y equals mx plus b, because we know that the line of best fit is a straight line, and we know the form of straight line is y equals mx plus b. So that's why we are using m and b, which are the slope and y-intercept, to print the best line. And then what we're going to do is we're going to be printing the slope and y-intercept based upon these points over here. So now what we're going to do is we're going to try to make predictions for the line of best fit. So XL is basically the leftmost point on the X axis, and that is 4.8. XR is the rightmost point on the X axis, that's 22.5. So we do have a corresponding, our corresponding features. So now we just need, we need our corresponding labels. And we need to also reverse that as well. So labels to features and features to labels, as we know that they're both really interconnectedly connected. So now what we can do is we need to figure out the value of YL and YR using our features, using our labels from the XL and RL. So now what we can do is we can actually figure out these features by using the matplotlib library once again. And that's why it's so beneficial, because now we can actually effectively figure out the features. So in order to do this, I'm just going to do the plt.plot function, and we're just going to plot the XL, XR, and then YL, YR. We're going to plot those points, and then we're going to do plotting of XY, which are the XY coordinates, and then KO just to give us the points, and the marker size of 2 just for those points as well. So now we can see that the line is on top of the points, and now we can see a very accurate representation of our model for line of best fit. So from this, if we want to figure out more corresponding features from our labels, we can easily just plug that into the X value. So let's say that we want our population to be 15,000. So if our population is 15,000, what will our profit be? So essentially, using the line of best fit and the accurate representation of our data points, basically the Python code will compute for you an accurate representation of the model, and will compute for you the specific corresponding feature as well. So essentially we have, when it's 15,000 as population, profit is around 13, or actually around 14,000 in this case, and it's able to just predict this using the line of best fit and our model. So that's essentially all we have for today's tutoring session. And I just want to thank everyone so much for attending today's tutoring session. I hope everyone enjoyed and was able to learn a lot about data sets, Python libraries, and most importantly, linear regression, and finding our line of best fit using the two methods of mathematical representation and Python, as well as Python libraries as well. And hopefully you guys understood the very important use of these libraries and how much easier it does make your computations in Python. So that's why Python is such a great language, because it does provide you all of these libraries and features that you can use. And hopefully everyone understood the concepts of features and labels, and of X and Y values, and why those are also so crucial as well. And of course, real life representations in the field of data science using linear regression. And that can basically range from anywhere from cancer prediction to stock prediction to even like house market prediction. So these are all things that can be predicted using linear regression and finding our line of best fit, and finding the model that best accurately represents our data points. So thank you everyone so much once again for attending. I hope everyone enjoyed this tutoring session, and I hope to see you guys in the next tutoring session. Thank you and have a great weekend.